In 1964, Fortune magazine ran a glowing feature on Sears Roebuck, hailing it as an extraordinary powerhouse of managerial excellence. Sears accounted for over 2% of all retail sales in the United States, pioneering game-changing innovations like supply chain management, store brands, mail-order catalog sales, and proprietary credit card systems. Observers remarked that everyone in the Sears organization simply did the right thing, easily and naturally. Yet just 3 decades later, Sears Merchandise Group posted a staggering loss of $1.3 billion in a single year, prior to a $1.7 billion restructuring charge. The world's most admired retailer had been systematically dismantled, not by incompetence, but by ignoring the rise of low-cost discount retailing and home centers, the exact lower-margin formats that stripped Sears of its core franchise. At that exact same time, a parallel tragedy played out in high technology. Digital Equipment Corporation, known as DEC, created the mini-computer market and was celebrated in 1986 as an unstoppable juggernaut. Business writers warned that taking on DEC was like standing in front of a moving train. Yet within 8 years, DEC was characterized as a company in desperate need of medical triage, its core sales drying up as it squandered years attempting halfway measures to respond to low-margin personal computers. These are not isolated stories of arrogant or lazy executives. Xerox dominated high-volume copying centers, but missed the explosion of tabletop copiers. Not a single integrated steel manufacturer in the world built a plant using low-cost mini-mill technology, even as mini-mills captured 40% of the North American steel market. Out of 30 manufacturers of cable-actuated power shovels, only 4 survived the transition to hydraulic excavators. In every single case, the decisions that led to failure were made while these companies were widely regarded as the best-managed firms in the world. This presents a terrifying paradox. The widely accepted principles of good management, listening closely to your best customers, investing aggressively in higher-performing products that promise superior profit margins, and systematically allocating capital to where returns are highest, are precisely the mechanisms that sow the seeds of ultimate corporate failure. This is the central thesis of Clayton M. Christensen's work, The Innovator's Dilemma. To understand why great companies stumble, one must first recognize the fundamental distinction between 2 categories of technological change: sustaining innovations and disruptive innovations. Sustaining technologies improve the performance of established products along the exact dimensions that mainstream customers in major markets have historically valued. They can be incremental refinements or discontinuous, radical breakthroughs, but their defining feature is that they give existing customers a better version of what they already buy. Disruptive technologies, by contrast, bring a completely different value proposition to the market. Initially, disruptive products offer worse performance along mainstream metrics. They are generally simpler, smaller, cheaper, and more convenient to use, but they yield lower gross profit margins and are commercialized in emerging or fringe markets that mainstream customers initially reject. The core dynamic driving failure is performance overshooting, driven by the desire to earn higher profit margins and beat competitors. Established suppliers improve product performance along a steep trajectory. In doing so, they frequently overshoot what mainstream markets actually need or are willing to pay for. This leaves a vacuum at the lower end of the market. An entering company wielding a disruptive technology enters at the bottom, serving fringe buyers. While initially inferior, the disruptive technology improves along its own rapid trajectory until it satisfies the baseline demands of the mainstream market. At that precise point of intersection, the the entrant invades the mainstream market, displacing the industry incumbent with stunning speed. Actionable key takeaways. First, audit your product portfolio to separate sustaining improvements from disruptive experiments. If every project in your pipeline is designed to serve your most profitable existing customers, you are completely unshielded from lower-end disruptions. Second, map customer performance demand against your technological development trajectory. Identify whether you are oversupplying functionality or performance attributes that mainstream customers no longer value or refuse to pay extra for. Third, establish different operational criteria for evaluating emerging technologies. Do not force low-cost, lower-margin disruptive ideas to pass the same hurdle rates and financial metrics required by your established core business. The business world's fruit fly. Lessons from the hard disk drive industry. To prove that good management directly causes corporate collapse, Christensen turned to an industry that Harvard Business School Dean Kim B. Clark described as the fruit flies of the business world, the hard disk drive industry. Just as geneticists study fruit flies because generations are born, mature, and die within a single day, researchers study disk drives because market segments, technological architectures, and multi-billion-dollar companies emerge and collapse across compressed multi-year cycles. A hard disk drive is an intricate electromechanical device. It consists of magnetic read-write heads mounted on an actuator arm that swings over flat aluminum or glass platters coated with magnetic material. A spin motor rotates the disks, while the actuator motor positions the head over concentric tracks. By rapidly alternating the polarity of electrical current through the head's electromagnet, positive and negative magnetic domains are created on the spinning platter, representing binary ones and zeros. The industry was born at IBM between 1952 and 1956, with the development of the Ramac drive, a machine the size of a large refrigerator that incorporated 50 24-inch platters to store just 5 megabytes of data. Over the next several decades, two primary non-captive markets emerged. The plug-compatible market, selling copies of IBM drives directly to IBM users, and the original equipment manufacturer market, selling drives to independent computer builders like Wang, Prime, and Digital Equipment Corporation. The pace of technological change in disk drives was relentless. Recording density grew by 35% per year, jumping from 50 kilobits per square inch in 1967 to 1.1 gigabits by 1995. Physical volume shrank by 35% annually, reducing a 20 megabyte drive from 800 cubic inches in 1978 down to 4 cubic inches by 1993. The industry's experience curve possessed a 50% slope, meaning that for every doubling of cumulative terabytes shipped, the cost per megabyte fell to 53% of its former level, a price drop of roughly 5% every single quarter for 20 years. Faced with this frantic pace, popular business theory suggested the technology mudslide hypothesis, the idea that established leaders failed because they simply could not keep pace with difficult, fast-moving technology. But Christensen's rigorous database of every disk drive model introduced worldwide between 1975 and 1994 proved this hypothesis entirely false. In every single case of sustaining technological change, no matter how complex, expensive, or radically novel, established industry leaders beat out entrant firms. Consider the transition from oxide disc coatings to thin-film metal platters, or the shift from conventional ferrite read-write heads to thin-film heads etched photolithographically. Developing thin-film heads required over 8 years of effort and more than $100 million in capital investments from industry incumbents like IBM, Control Data, and digital equipment. When thin film heads emerged, established firms led the commercialization, while startups attempting to use thin film heads failed. The same pattern repeated when next-generation magneto-resistive heads were introduced. Industry leaders like IBM, Seagate, and Quantum spearheaded the transition. Incumbents did not fail because they lacked technological prowess, risk tolerance, or R&D investment. They failed exclusively when confronted with simple, architecturally disruptive innovations that reduced physical drive size. In the mid-1970s, 14-inch drives with removable disk packs dominated the mainframe computer market. In 1978, entrant firms including Shugart Associates, Micropolis, Priam, and Quantum introduced 8-inch drives. Mainframe manufacturers explicitly rejected 8-inch drives because they offered only 10 to 40 megabytes of capacity, whereas mainframes demanded 300 to 400 megabytes. Listening to their customers, 14-inch drive makers ignored the 8-inch architecture. Instead, 8-inch entrants found a new emerging market: mid-sized minicomputers built by DEC, Wang, and Hewlett-Packard. Minicomputer buyers needed smaller physical dimensions and were willing to pay a premium for small footprint drives, even though the cost per megabyte was higher. Once established in minicomputers, 8-inch drive makers improved drive capacity at 40% per year, far faster than the 25% annual capacity growth demanded by minicomputer users. By the mid-1980s, 8-inch drive capacities intersected the lower-end needs of mainframes. Because 8-inch drives were cheaper, smaller, and had better mechanical vibration characteristics, they invaded the mainframe market from below. 2/3 of the established 14-inch drive makers never even introduced an 8-inch product, and the remaining 1/3 introduced models 2 years behind the entrants. Ultimately, every single 14-inch drive maker was driven out of the OEM market. This destructive cycle repeated itself with clockwork precision. In 1980, Seagate Technology launched the 525-inch drive with capacities of 5 and 10 megabytes. Minicomputer makers rejected it, demanding 40 to 60 megabytes. Seagate sold its disruptive drives into the newly emerging desktop personal computer market. 5.25 drive capacity grew at 50% per year, eventually crossing into minicomputer performance requirements. Half of the 8-inch drive manufacturers never introduced a 5.25-inch model, and of the 4 major 8-inch leaders, Shugart, Micropolis, Priam, and Quantum, only Micropolis survived. In 1984, Scottish entrant Rodeem introduced the 3.5-inch drive, followed in 1987 by Connor Peripherals. Connor engineered a rugged, lightweight 3.5-inch drive that consumed low power. Seagate's engineers had actually developed working 3.5-inch prototypes as early as 1985. However, when Seagate marketers showed the prototypes to lead customers like IBM's PC division, those mainstream desktop PC clients rejected them. IBM wanted 40 to 60 megabytes for its next-generation desktop machines, while the 3.5-inch drive could only offer 20 megabytes at a higher cost per megabyte. Seagate's executives rationally cancelled the 3.5-inch program to focus resources on higher-margin 5.25-inch drives. Meanwhile, Connor Peripherals partnered with Compact Computer, securing a $30 million investment. Connor sold its 3.5-inch drives into a brand-new application, portable and laptop computers. In its first year of operation, Connor booked $113 million in revenue, a historic record for an American manufacturing startup. By 1988, when 3.5-inch drive capacities finally reached desktop requirements, Seagate was forced to launch 3.5-inch drives defensively. shipping them with adapter brackets to fit inside desktop computer frames. The pattern repeated yet again with two 5-inch drives introduced by Prairie-Tech in 1989 and dominated by Connor in 1990 for notebook computers, and 1.8-inch drives in 1992, where entrant startups captured 98% of the $130 million market by finding their initial home in portable heart monitoring devices. Actionable key takeaways. First, recognize that listening blindly to your current lead customers will cause you to miss disruptive shifts. Lead customers pull you along your existing trajectory and actively discourage investment in simpler, lower-capacity innovations. Second, do not evaluate a new architecture based on mainstream performance criteria. Look for emerging or fringe applications where the unique attributes of the new technology, such as smaller physical size, lower weight, or ruggedness, are highly valued. Third, beware of high growth rates in technological capability. If an emerging technology is improving performance faster than mainstream market demand is growing, assume it will eventually invade your core business. The physics of failure, value networks and organizational forces. To explain why competent managers repeatedly make decisions that lead to their own demise, we must look beyond organizational flaws or capability deficiencies. Some scholars, such as Rebecca Henderson and Kim Clark, argued that organizational structure impedes innovation because a firm's development teams are structured around product components. They excel at component innovations, but fail when architectural changes require new communication channels. This structural reflection was famously illustrated in Tracy Kidder's The Soul of a New Machine, where data general engineer Tom West examined the interior layout of a competitor's minicomputer and declared he could see Digital Equipment Corporation's organizational chart in the design of the physical machine. Other scholars, including Philip Anderson and Michael Tushman, focused on competence-destroying versus competence-enhancing technologies, arguing that incumbents fail when a new technology destroys the value of their accumulated historical skills. However, Christensen identified a deeper, overarching structural concept that explains both the success and failure of firms: the value network. A value network is the commercial context within which a firm identifies and responds to customers' needs, solves problems, procures inputs, reacts to competitors, and strives for profit. Just as a physical product is built as a nested hierarchy of components, where an MES system contains a mainframe contains a disk drive contains read-write heads, and heads contain thin film alloys. Companies are embedded in nested commercial networks of suppliers, integrators, and end users. Boundaries of value networks are defined by unique metrics of value. Using hedonic regression analysis on thousands of disk drive models, Christensen quantified how different value networks priced specific product attributes. In 1988, mainframe computer buyers were willing to pay $1.65 for an incremental megabyte of disk capacity. In mini-computers, that shadow price dropped to $1.50 per megabyte. In desktop PCs, $1.45 per megabyte. And in portable computers, just $1.17 per megabyte. Conversely, portable and desktop buyers paid a significant premium for physical volume reduction, an attribute that mainframe buyers valued at exactly $0. Crucially, each value network carries a distinct, inherent cost structure. Competing in the mainframe network required massive R&D outlays, customized low-volume manufacturing overhead, and extensive direct sales and field service forces. Consequently, mainframe makers and their 14-inch disk drive suppliers required gross profit margins of 56 to 60% to survive. By contrast, the mini-computer value network operated on 40% gross margins. The desktop PC value network operated on 25% gross margins. The portable computer value network, relying on standard components and retail distribution, operated profitably on 15 to 20% gross margins. This cost structure asymmetry creates a powerful directional bias. Established firms find it financially attractive and rational to migrate upmarket into higher-tier value networks that offer higher gross margins. However, they are functionally incapable of allocating capital downmarket into lower-tier value networks characterized by low gross margins and smaller initial transaction sizes. When a disruptive technology emerges, it cannot satisfy the performance metrics or profit requirements of the incumbent's value network. Therefore, resource allocation systems within well-managed firms automatically starve disruptive projects of funding, diverting capital toward sustaining projects that serve high-margin mainstream clients. Actionable key takeaways. First, calculate the gross margin requirements built into your company's corporate cost structure. Realize that your current cost structure makes lower margin, disruptive opportunities look financially unviable to your executive board. Second, map the nested value network of your industry. Identify which peripheral value networks exist around you that prioritize completely different performance metrics, such as portability, simplicity, or low unit cost. Third, avoid using standard corporate hurdle rates when evaluating projects targeting lower-tier value networks. If you evaluate a $10 million low-margin opportunity using a cost structure built for a $1 billion high-margin business, you will reject every single disruptive growth engine. The 6-step pattern of incumbent failure. Across every industry affected by disruptive innovation, established firms follow a predictable, step-by-step path toward failure. Through detailed interviews with over 80 executives who managed key industry transitions, Christensen reconstructed the exact decision-making sequence that leads good companies to ruin. Step 1. Disruptive technologies are first developed within established firms using bootlegged resources. Contrary to popular belief, disruptive innovations rarely originate in startup garages. Engineers inside leading companies build the initial prototypes, often using standard off-the-shelf components. Seagate's engineers built 80 working prototypes of 3.5-inch drives in 1985 before ever seeking formal project approval. Control Data engineers designed working 8-inch drives 2 years before they appeared in the market. Step 2. Marketing personnel seek reactions from lead customers. Marketers take the prototype drives to their firm's most important, highly profitable accounts. Seagate showed its 3.5-inch drives to IBM's desktop PC division. IBM's engineers explicitly rejected the 20-megabyte 3.5-inch drive because they needed 40 to 60 megabyte 5.25-inch drives for their upcoming product lines. Faced with zero interest from major accounts, marketers draft pessimistic sales forecasts. Financial analysts calculate lower projected gross margins, and management shelves the project. Step 3. Established firms step up the pace of sustaining technological development. In response to lead customer demands, executives reallocate engineering resources toward high-margin sustaining projects. After shelving the 3.5-inch drive, Seagate dramatically accelerated its 5.25-inch product launches, increasing new model introductions by 57% in 1985, 78% in 1986, and 115% in 1987. They incorporated complex, high-risk sustaining technologies like thin-film disks, voice coil actuators, RLL recording codes, and embedded SCSI interfaces. These decisions were starkly rational, competing for $500 million in 5 25-inch drive sales at 35 to 40% gross margins was infinitely superior to chasing a speculative $50 million 3.5-inch laptop market with uncertain margins. Step 4. New companies are formed, and markets for disruptive technologies are found by trial and error. Frustrated engineers leave the established firms to found startups. Connor Peripherals was formed by disaffected employees from Seagate and Miniscribe. Micropolis was founded by former Pertec executives. Shugart and Quantum were created by engineers who defected from Memorex. These startups cannot sell to traditional computer makers either, so they aggressively probe new applications through trial and error, ultimately discovering new customer bases like desktop PCs, laptops, or portable devices. Step 5. Entrants move upmarket. Once established in their home value network, startups adopt sustaining component innovations, driving a 50% annual growth trajectory in product performance. As their performance improves, entrants look upmarket toward the higher volumes and richer profit margins of the mainstream market. The view is asymmetrical. Established leaders see lower-tier markets as unprofitable, while entrants see higher-tier markets as lucrative opportunities. Eventually, the disruptive technology intersects the performance demands of the mainstream market. Mainstream buyers adopt the new architecture because it has become cheap, small, fast, and reliable. Step 6. Established firms belatedly jump on the bandwagon to defend their customer base. As entrants invade the mainstream market, incumbents pull their old prototypes off the shelf and launch defensive products. However, the entrant firms have already secured insurmountable manufacturing cost advantages and deep design experience. Entrants bring cost structures built for lower gross margins, triggering brutal price wars. Established firms find that survival is their only reward. They fail to capture meaningful market share in the new domain, and their new products merely cannibalize their remaining legacy sales. Actionable key takeaways. First, decouple your disruptive innovation efforts from mainstream sales and marketing teams. Never rely on mainstream sales personnel to evaluate or sell a disruptive technology, because they will always prioritize high-volume, high-margin legacy clients. Second, embrace a trial-and-error discovery process for initial customer targeting. Understand that the ultimate market for a disruptive technology cannot be known in advance. You must aggressively test multiple non-traditional user groups. Third, monitor employee defections and internal bootlegged projects. When senior engineers defect to commercialize an internal prototype that was rejected by marketing, treat that event as an urgent warning indicator of imminent industry disruption. Testing the theory, flash memory, and the 5 fundamental principles. The predictive power of Christensen's value network framework is starkly illustrated by the emergence of solid-state flash memory. Flash memory is a semiconductor technology that retains data on silicon chips without requiring continuous electrical power. Flash is fundamentally disruptive relative to electromechanical disk drives. It consumes less than 5% of the power of a disk drive and possesses no moving parts, making it exceptionally rugged. However, flash memory carries significant disadvantages. Its cost per megabyte was 5 to 50 times higher than disk storage, and its chips wear out after a few 100,000 write cycles. Initially, flash memory could not compete in mainstream computing. Instead, it found a home in non-computing value networks, such as cellular phones, heart monitors, modems, and industrial robotics, where individually packaged socket flash chips grew to a $1.3 billion market by 1994. When credit card-sized flashcards emerged in the early 1990s using standard SCSI controller interfaces, Analysts predicted that solid-state flash would rapidly replace hard disk drives in notebook computers. Why did leading disk drive manufacturers like Seagate and Quantum fail to dominate the emerging flash card market? A capabilities perspective would suggest that drive makers lacked semiconductor expertise, but drive makers had already built deep capabilities in custom integrated circuit design and ASIC chips, partnering with external silicon foundries. Seagate invested in Sun Disk Corporation, designing custom chips fabricated by Matsushita and assembled in Korea. Quantum partnered with silicon storage technology. The true barrier was not technological capability, it was the value network. In 1995, a typical notebook computer required roughly 350 megabytes of mass storage. Providing 350 megabytes of flash memory cost 50 times more than a comparable 2.5-inch hard disk drive. Flash had no value on a desktop PC where power and ruggedness commanded zero price premium. Because disk drive executives could not deploy flash memory profitably inside their existing core value networks, their resource allocation systems naturally diverted capital back toward mainstream disk drive development. To successfully navigate these powerful structural forces, managers must master the 5 laws of disruptive technology. Principle number 1. Companies depend on customers and investors for resources. Under resource dependence theory, published by Jeffrey Pfeffer and Gerald Salancic, managers do not have freedom to allocate capital as they please. Customers and investors control corporate resource allocation because projects that do not satisfy customer demands are killed. To succeed with a disruptive technology, executives must create an independent, autonomous organization that is free from mainstream client demands and positioned within a user base that actually wants the disruptive product. Principle number 2. Small markets don't solve the growth needs of large companies. As a company grows, its revenue growth requirements escalate. A $40 million company needs only $8 million in new revenue to grow 20%, whereas a $4 billion company requires $800 million in new revenue. Emerging disruptive markets are initially tiny, producing $10 million to $30 million in sales. Large established firms cannot justify focusing top management attention or capital on markets that do not move the corporate growth needle. To harness this principle, large companies must embed disruptive projects within small, agile organizational units whose size matches the size of the target market. Principle number 3. Markets that don't exist can't be analyzed. Standard market research and rigorous financial projections are invaluable for sustaining innovations in existing markets. But when dealing with disruptive technologies in non-existent markets, traditional market research is consistently wrong. Demand for quantification paralyzes managers. Instead of execution-based planning, managers must utilize discovery-based planning, assuming that initial forecasts and strategies are inherently wrong, and designing low-cost experiments to learn what needs to be known. Principle number 4. An organization's capabilities define its disabilities. An organization's capabilities reside in its processes, how labor, material, and information are transformed into higher value, and its values, the prioritization criteria managers use to make decisions. While individual employees are highly adaptable, organizational processes and values are inherently rigid. A process optimized for high-volume, high-margin manufacturing cannot function effectively in low-volume, low-margin emerging markets. When confronting disruption, managers must create new capabilities by establishing autonomous, spin-off entities or acquiring small organizations with matching processes and values. Principle number 5. Technology supply may not equal market demand. Products that underperform mainstream market demands today will eventually overshoot what mainstream markets require tomorrow. As product performance passes market demands, the fundamental basis of competition shifts. Buyers no longer choose products based on raw functionality. Instead, competition shifts through a predictable life cycle sequence from functionality to reliability, then to convenience, and ultimately to price. Companies that track these shifting performance metrics can anticipate when disruptive lower-cost competitors will invade their core markets. Actionable key takeaways. First, establish a completely independent or autonomous spin-off unit for every disruptive project. Grant that unit total freedom over its cost structure, sales process, and resource allocation, ensuring it is geographically and operationally isolated from the legacy organization. Second, implement discovery-based planning rather than traditional corporate forecasting. Set milestones based on learning speed and hypothesis testing rather than short-term revenue output or market share metrics. Third, continuously measure whether your current product's performance is overshooting what your mainstream customers can actually absorb. When customers stop using new functional upgrades and begin prioritizing reliability, convenience, or price, prepare immediately for a lower-cost, disruptive attack from below.